Welcome to section 2.3, Quadratics in Standard Form. So in the last two sections of this unit, we've talked about the quadratic equation in vertex form, and we've talked about it in intercept form. Now we're going to talk about it in standard form, which is the form that you're most likely to encounter in most cases. So the quadratic function in the form f of x equals ax squared plus bx plus c, this is called standard form. And it's called standard form because the terms of the polynomial are arranged in order of highest exponent to lowest. And here I've given it to you in this gray box here, just so you can have it in one place where you can easily find it. The a is the coefficient of the quadratic term, b is the coefficient of the linear term, and c is your constant. Now the axis of symmetry, as with the last two forms, can be found by using a particular formula. And that formula is x equals negative b over 2a. So all you have to do is find your b, find your a, plug them in, and you can find what your x coordinate is for your vertex, and that happens to be your axis of symmetry. So, as I just stated, that is also the x coordinate of your vertex. You take that x coordinate, put it back into your original function, you'll find your y coordinate of your vertex. And as always, the y-intercept can be found if you plug in 0 for x. Well, if you plug in 0 for x, what happens to the first term? Well, it becomes 0. The second term also becomes 0. So all you're left with is c. So f of x equals c is your y-intercept. It will always be the c value because the other two have x in them, and both of those terms are both going to go to 0. So your y-intercept will always be c. Okay, now let's use standard form to do a few things, okay? And we're going to use it to identify some key features. So let's start off with this first example and identify the axis of symmetry, the vertex, and the y-intercept, and then we'll graph the function. So here we're given a quadratic equation in standard form. Our axis of symmetry can be found using x equals the opposite of b over 2a. Well, here b is negative 4, and then a is 1. So you end up with 4 over 2. So our axis of symmetry is 2. Now we just have to plug 2 in to find what our vertex is. So you have 2 squared minus 4 times 2 plus 5. So that's going to be 4 minus 8 plus 5, which ends up being 1. And so our vertex is at 2, 1. And our y-intercept's very easy to find. It's just our c value. So it's 0, 5. So let's plot this. Our vertex is 2, 1, so over 2, up 1. And our y-intercept's at 0, 5, so we're just going to go up 5 on the y-axis. And if we use our axis of reflection, or our axis of symmetry, we can reflect across it. Now we have 3 points. Now, a couple of things here. First of all, we know what our stretch and compression are because just like with the others, then we can use a to figure out what stretch and compression is. So a behaves just like it did in the other forms, in intercept and vertex form. So out in front, this number is going to dictate if it's stretched or compressed. Well, since it's 1, it's going to be a standard form parabola. And since it doesn't have a negative in front of it, it's also going to be concave up. So we have 1, 1 here and 1, 1 here reflected. And we can also do 3, 9. So 3 up over 3, up 9, over 3, up 9. And that gives us a sufficient number of points to graph our parabola. Again, like I mentioned in the last two videos, I will not attempt to do the sketch. You can kind of clearly see from the plotted points what the parabola will look like. You are free to do that sketch for yourself. Okay, let's do a few more examples, and we're going to kind of run through these examples fairly quickly because they all ask for the same thing. We're just going to kind of get some repetition in and some practice. So the axis of symmetry is x equals negative b over 2a. B in this case is negative 8. A is negative 1. So we have negative 8 over 2, which is going to be negative 4. So we take that negative 4, plug it into our equation. So we have negative 4 squared minus 8 times negative 4 minus 20. Negative 4 squared is 16, but we have a minus out in front, so we got negative 16. Negative 8 times negative 4 gives us positive 32. And then we have a minus 20. And when you do all that math, you end up with negative 4. So our vertex is going to be at negative 4, negative 4. And our y-intercept, we read it off of our c term. Our y-intercept is going to be negative 20. Well, our y-intercept really doesn't do us much good on this graph because we have a 10 by 10 graph. But we do have the vertex, so we'll plot that. Negative 4, negative 4. And we can also figure out what this parabola is going to look like if it's concave up or concave down using our a term. Well, it's negative, so we know it's going to be concave down, but it's also a negative 1, which means it won't be compressed or stretched. So we can do over 1, down 1, over 2, down 4, and that gives us the 5 points needed to sketch our parabola, and really we run out of graph anyway. Okay, let's move on to C. Our axis of symmetry is going to be x equals negative b over 2a. So b here is negative 4. A is negative 2. So we're going to end up with negative 4 over 4, which is negative 1. Let's plug that into our original to find out what the vertex is, what the y-coordinate of the vertex is. So we got negative 2 times negative 1 squared minus 4 times negative 1 minus 4. So we have negative 1 squared is 1 times negative 2 is negative 2. Negative 4 times negative 1 is positive 4 minus 4. So we end up with negative 2. So our vertex is at negative 1, negative 2, and our y-intercept, reading the c term, is 0, negative 4. So let's plot our vertex, negative 1, negative 2, which would go here. Our y-intercept is 0, negative 4, so that goes here. And we can reflect that across the axis of symmetry. And we can already tell we're going to have a stretch. We know that from that first term. We know it's going to be concave down. We know it's going to have a stretch factor of 2. So we went over 1, down 2. That confirms. So we're going to go over 2, down not 4, but 8. So 1, 2, 3, 4, 5, 6, 7, 8, which takes us to the edge of the graph. And those would be the 5 points that we would need to graph this parabola. Moving on to D. Our axis of symmetry, we have x equals minus b over 2a. Our b here is negative 18. Our a is 3. So we're going to have 18 over 2 times 3 is 6. So 18 divided by 6, that gives us 3. Now let's plug that 3 in to find our y value for our vertex. Okay, so we have 3 squared, which is 9. 9 times 3 is 27. 18 times 3 is 54. And then we have plus 20. And when you add and subtract all those numbers together, you get negative 7. So our vertex is at 3, negative 7. And our y-intercept is 0, 20 from that c value. Again, that y-intercept not going to do us much good, but we do have the vertex. So we have 3, negative 7, 1, 2, 3, 4, 5, 6, 7. So that gets plotted right there. Now let's see about that number out in front. So we know it's going to be concave up because it's positive, but we are stretching by a factor of 3. So we're going to go over 1 and up 3. And then we're going to go over 2, and instead of up 4, we're going to go up 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we can reflect both of these points on the other side of the axis of symmetry. And those are the points that you need to be able to draw a reasonable parabola. Okay, let's move on to a couple more examples, and these examples are going to be just a little bit more challenging. Okay, so this example, let's start off with our axis of symmetry. X equals negative b over 2a. Well, b here is negative 5, and a is 1. So we're going to have 5 over 2 as our x-coordinate for our vertex. And now let's see if we can find what the y-coordinate is going to be. Well, we're going to plug this in. So we're going to have 5 halves squared minus 5 times 5 halves plus 8. All right, 5 halves squared is 25 over 4. And then we're going to have minus 5 times 5 is 25, so we have 25 over 2. And we still have plus 8 out here. So now let's find a common denominator. So our common denominator is going to be 4. So we're going to have 25 over 4 minus, this is going to be 50 over 4 if we multiply the top and bottom by 2. And then 8 times 4 is 32, so that gives us 32 over 4. And all of that together gives us 7/4. So our vertex is going to be at 5 halves, 7/4. Not really that useful of information. We can graph that, but the most important thing is we know what our axis of symmetry is. And let's go ahead and try to attempt to graph this. Well, first let's get our x-intercept, which that's 0, 8 from our c value. All right, so we know 5 halves is 2.5, so we're going to go over to 5 halves here, which is 2.5, and then we're going to go up by 7/4, which is just shy of 2. So there's 4/4, which is 1, and then another 3 past that. So you're going to be right about here with your vertex. Now let's graph our y-intercept. So we know we have 0, 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay? And then we're going to have the same on the other side. So we're 2.5 from this side, so we're going to go over 2.5 and go over to 8. So there's 3 points that we can use. Well, let's see what happens when we plug in 1 for x, okay? Because we know we want to plot something that's in between here. If we plug in 1 for x, well, then you can do 1 squared, which is 1, minus 5, which is negative 4, plus 8, which gives you 4. So you know you're going to have a point at 1, 4. And you can reflect that on the other side. And there is 5 points for you, okay? So if you're ever looking for points, you can always try to plug it in on standard form and see what you get. We could do the same with 2. If you plug in 2 in here, you get 2 squared, which is 4, minus 10, which is negative 6, plus 8, which is 2. So you would end up with a plot here, and then you reflect it over here. And so now we've got plenty of points to graph our parabola. All right, let's look at one last example. And again, this one's going to be a bit of a beefier example for you. So let's start off with the axis of symmetry. X equals negative b over 2a. Well, b here is 6, and a is negative 2. And so you've got 6 over 4, which can be reduced down to 3 halves. So again, we're going to be dealing with some fractions here. Let's see if we can find the y value of our vertex. You've got negative 2 times 3 halves squared plus 6 times 3 halves minus 5. We've got negative 2 times, that's going to be 9/4 plus 6 times 3, and let's go ahead and multiply that too, okay? So negative 2 times 9/4, that's going to give you negative 18/4. Then we have 6 times 3, which is 18, so you're going to have 18 halves. And then minus 5. Let's get a common denominator. So we're going to have negative 18/4. Double the top and the bottom here. You're going to get plus 36/4. And then 5 times 4 is 20, so you got negative 20/4. So that's going to give you negative 2/4, which is negative 1/2. So our vertex is going to be at 3 halves, negative 1/2. And then our y-intercept is going to be at 0, negative 5 from our c value. All right, well, let's plot our vertex. We've got 3 halves, so that's 1.5, and then negative 1/2, so that's going to be right here. And then our x, or I should say our y-intercept is going to be at 0, negative 5, so 1, 2, 3, 4, 5. And we can reflect that across the axis of symmetry. We know it's going to be concave down. We know where our stretch is going to be, but we can find another point by just putting in 1. So let's put in 1. So the first we get negative 2 plus 6, which is 4, minus another 5 is going to give you negative 1. So you can go 1, negative 1. There's a point there, and you can reflect it there. All right, let's put in negative 1 and see what we get. Well, if we put in negative 1, I believe we're going to run off the graph because we'll end up with negative 1 squared, which is 1. So you end up with negative 2 here, minus 6, which is negative 8, minus another 5 gives you a, let's see, what do we have here? We had negative 2 minus 6, which is negative 8, minus another 5 gives you negative 13, and that will run us off the graph. So we have enough points here. We have 5 that we can reasonably graph our parabola. Okay, well, a quadratic equation can be written if you're given 3 points. So what we're going to do is we're going to go through the process of, if you're given 3 points, how can we use standard form to write our quadratic equation. So what we're going to do is we're going to start off by using these 3 points, okay? And we'll do this in this example here. We're going to start with these 3 points, and we're going to plug each set of coordinate pairs into the standard form of the quadratic equation. So we're going to have first, for the first point, y is negative 1, so you got negative 1 equals, and then you have 0 for x, so you're going to have a times 0 squared plus b times 0 plus c. Then for the second one, y is 4, so you're going to have 4 equals a times 1 squared, because x is 1, plus b times 1 plus c. And then for the third one, you're going to have 8 equals a times negative 3 squared plus b times negative 3 plus c. And for all 3 of these, I'm going to clean them up a little bit. Well, the first one cleans up very nicely and becomes just negative 1 equals c. For the second one, we have 4 equals, 1 squared is just 1, so you have a, then plus b, plus c. And then for the last one, you have 8 equals, negative 3 squared is 9, so you have 9a. And then minus 3b plus c, okay? Now, we know that c is negative 1, so we're going to substitute that into the other 2, and then we are going to solve a system of equations here. Okay, so we are going to have 4 equals a plus b minus 1. And we'll have 8 equals 9a minus 3b minus 1. So if we add 1 to each side on both of these, you get 5 equals a plus b. On this one, you'll get 9 equals 9a minus 3b. So let's solve this first one for a. So let's subtract b from each side. You get 5 minus b equals a. And we're going to plug that into the other one. So we're just going to use simple substitution to solve this. So a is 5 minus b, and then we have 3b. So 9 equals 45 minus 9b minus 3b. 9 equals 45 minus 12b. Subtract 45 from each side, you get negative 36 equals negative 12b. And so you get b equals 3. All right, so we're going to substitute 3 in on our other equation for b. 5 minus 3 is 2, so a is 2. So we can write our final answer as, in our standard form, y equals a is 2, so 2x squared, b is 3 plus 3b, and then c is negative 1 minus 1. And that would be our equation, our quadratic equation that goes through all 3 of the points that were given at the top here. Okay, let's do another example of this. So here we have 3 points, and we're going to find the standard form of the quadratic equation that goes through all 3 of these points. So we start with y equals ax squared plus bx plus c, and we're going to plug in. So y is 7 for the first one, x is 0. Eight is y for the second one, and x is negative 1. And then for the third one, y is negative 1, and our x is 2. And if we clean all 3 of those up just a bit, then we're going to be left with 7 equals c. We have 8 equals a minus b plus c. And then we have negative 1 equals 4a plus 2b plus c. Well, we know that 7 is c, so let's use that so we have a system of 2 equations to solve. Okay, so if we subtract 7 from each side, we get 1 equals a minus b. And let's go ahead and solve this for a. So we have 1 plus b equals a. All right, we subtract 7 from each side on this one. We get negative 8 equals 4a plus 2b. And then we have a is 1 plus b, so we're going to substitute that in. 1 plus b plus 2b. Negative 8 equals 4 plus 4b plus 2b. Subtract 4 from each side, you get negative 12 equals, and then combine our b's, so we have 6b. Divide by 6, you get negative 2 equals b. Substitute that in for your b up here. 1 minus 2 is a, so negative 1 equals a. So now we can write our quadratic equation in standard form. Y equals negative x squared minus 2x plus 7. And we'll do one more example of this. Again, we're going to start with y equals ax squared plus bx plus c, which is just our standard form of our quadratic equation. And we're going to plug in. Y is 2 for the first one. So you have a times 0 squared plus b times 0 plus c. Negative 9 is our y for the second one. Negative 2 is our x. And then 30 is our y for the last one, and 4 is our x. And let's clean all three of these up. We get 2 equals c. We get negative 9 equals 4a minus 2b plus c. And then we get 30 equals 16a plus 4b plus c. So let's plug in what our c is on both of these. So we have 4a. Negative 9 equals 4a minus 2b plus 2. And you have 30 equals 16a plus 4b plus 2. Subtract 2 from each side, you get negative 11 equals 4a minus 2b. And then over here, we get 2, subtract 2 from each side, we get 28 equals 16a plus 4b. Now, I'm going to use a different method. Instead of substitution like on the last two, because things are not going to come out nice and even when we solve on this first one anyway, let's use elimination. So let's stack the first one. 28 equals 16a plus 4b. And if we want to stack the second one, we can multiply it by 2. Negative 22 equals 8a minus 4b. And we can eliminate our b's if we add these two equations together. So when we do that, 28 minus 22 gives us 6. 16 plus 8 gives us 24. Our b's cancel. 6 over 24 is reduced down to 1/4. So a is 1/4. Now let's go over and plug it back into one of these. And I'll plug it back into the second one here. So you have 16 times 1/4 plus 4b. 28 equals 16 divided by 4 is 4. Subtract 4 from each side. And then divide by 4. And you get that 6 is b. So we can write our final equation as y equals 1/4 x squared plus 6x plus 2. So you may find it useful to switch between different forms of the quadratic equation because the standard form may not give you what you need, the intercept form may not give you what you need, your vertex form may not give you what you need, so you need to get to a different form. So here we're going to talk about how vertex form and intercept form relate to standard form and how you can get to standard form. So this first part is going to be very mathy, but it is going to kind of give you an idea in terms of how you get from one to the other and that all three are related. It will feel much simpler once we do it with numbers, but here I'm just going to work with the variables that we have given to us in these different forms. So let's begin with the vertex form to standard form. So here we have vertex form, and it's presented to you as y equals a times the quantity x minus h squared plus k. So I'm going to do a few things. First, let's multiply out this x minus h squared. Okay, and if you know anything about binomial expansion, you know that you can square the first, then multiply the two terms, which gives you negative hx, and then double it, so negative 2hx. Then square this last term. Now if you want to, you can take x minus h times x minus h and FOIL it out, and you'll see that you get to the same thing right here. Now I'm going to distribute the a. So we have ax squared minus 2ahx plus ah squared plus k. And you'll notice right here in the front, we've already got ax squared, which is the first part of our standard form. So now we're going to pull the rest of it out. And we're going to do that by grouping things a little bit. So if we group things a little bit, we can have ax squared plus negative 2ahx plus ah squared plus k. Well, now I'm just going to let a equal a. Let's let b equal this negative 2ah. And let's let c equal ah squared plus k. And if I do that, then we end up with ax squared plus bx plus c. And now we're at standard form. This is referred to as a mathematical proof because we did not use any numbers. We used letters as stand-ins for the numbers or variables. We're going to do the same for intercept form to standard form. We'll start by multiplying out our two binomials. So that gives us x squared minus qx minus px minus pq. So the first, outer, inner, and last. Now I'm going to distribute the a. So we get ax squared minus aqx minus apx minus apq. And now I'm just going to group things together. We've got ax squared. I'm going to factor out a plus x and write what's left in the middle here, which is aq, or I should say negative aq, minus ap. And then we're going to do plus negative apq. And like I did before, let's let a equal a. Let's let b equal negative aq minus ap. And let's let c equal negative apq. And when we do that, we end up with y equals ax squared plus bx plus c. Then this shows you also that a behaves the same way in vertex form, intercept form, and in standard form because a equals a. So since a equals a is going to be the same in all three forms of the quadratic equation. Okay, so you may find it useful to know functions in vertex or intercept form that can be rewritten in standard form. Now I know this seems complicated, but when we go to these examples, it becomes much easier because we can simply rewrite things. So let's rewrite each function in standard form, and then we'll identify the values of a, b, and c. So let's start with a here. If we want to rewrite this, all we have to do is multiply our binomial. So we get x squared minus 6x plus 9 minus 4. We're going to distribute out our 2. So we have 2x squared minus 12x plus 18 minus 4. And then finally, we're going to do 18 minus 4 on the end. And that gives us plus 14. And now we have it in standard form, where a is 2, b is negative 12, and c is 14. So you'll notice it doesn't really take very long to convert it to standard form when you're dealing with numbers. Part B is just as easy. We're going to go from intercept form. So again, we're going to multiply out our binomials, x squared minus x plus 3x minus 3. We'll distribute our minus sign. Well, before we distribute the minus sign, let's combine our like terms. Minus x plus 3x gives us plus 2x. And now we'll distribute our minus sign. So we're going to have negative x squared minus 2x plus 3. And that's our standard form of our quadratic formula, where a is negative 1, b is negative 2, and c is 3. All right, let's move on to example 4. We can now write an equation in standard form for the graph that is given here. We can look at this graph and we can write an equation for it. And we don't need a graphing calculator to do it, and we don't need any other graphing utility to do it either. We can do it with the knowledge that we have from these last 3 sections. So we want to first look at one of two things. We either want to look for the x-intercepts or we want to look for the vertex. Well, the x-intercepts on this one really are not going to be of much use because we're not quite sure what the x values are. They're somewhere between 0 and 1 and 5 and 6, but we don't know specifically what those values are. But we do know what the vertex is, so we're going to use that so that we can write the equation in vertex form. So we've got the vertex at 3, negative 7. Now normally what we would do is we'd start with the vertex form, we'd find a point, and then we would determine what our a is. But since we have a graph, we can do some analysis and figure out what a would be anyway. First of all, we know it's positive because it's concave up. And if we just look at the graph, we can go over 1, up 1. All right, we've met the graph there. Over 2, up 4, we've met the graph there. Over 3, up 9, we meet the graph there. So it's not stretched or compressed, so we know that a is just going to be 1. So we'll start with vertex form. Y equals a times x minus h squared plus k. We know a is just 1, so we can just leave that off the front. And we know that h is 3. And we know that k is negative 7. So now it's just a matter of multiplying this out and simplifying. So we've got x squared minus 6x plus 9 minus 7. So y equals x squared minus 6x, 9 minus 7 gives us plus 2. And so there's our equation in standard form. Let's look at part B here. Example B. Well, we can use the vertex, but we also have the x-intercepts this time that are usable. So since we've already done one in vertex form, let's look at the x-intercepts. The x-intercepts are at 2, 0 and at 6, 0. So let's use the intercept form. Y equals a times x minus p times x minus q. And p and q are just our intercepts. So we're going to have, well, before we get to our intercepts, what is our a going to be? Well, if we look at our a, first of all, we know it's going to be negative because we're concave down. So let's do a little exploration here. We have 1 over 1 down. Okay, that checks. 2 over 4 down. Okay, so it looks like we're not compressed or stretched. So we're just going to have a minus sign out in front. And then we have x minus 2 times x minus 6. Y equals negative x squared minus 2x minus 6x plus 12. Combine our two middle terms on the inside. We've got negative 8x plus 12, and then we'll distribute our minus sign. So we have y equals negative x squared plus 8x minus 12. Okay, so the last thing I want to do in this section is we've talked about the quadratic function in vertex form, intercept form, standard form, and we started kind of working between the forms, and we can do all sorts of things now and identify all sorts of things with quadratics. So the last thing I want to do is now do some applications of quadratic functions. Quadratic equations can be used to model a variety of real-world situations, including throwing a ball or kicking a ball, launching a rocket, jumping forward. All of these forms of motions are types of projectile motion. Whatever is being launched or put into the air is your projectile. That can be a ball, that can be a rocket. If it's a person jumping, it can be a person. A person can be a projectile. The curve formed by the path of the object is, you know it, you love it, a parabola. Okay, so since the object's path is a parabola, that means we can use a quadratic equation to model that object's path. So here I've given you an example of a small rocket being launched, and on the y-axis is height, on the x-axis is time. Okay, so what we're going to do is we're going to use this graph to identify a few things. So first of all, what is the greatest height the rocket reaches? Well, if we look at the top here, this is the top height that it reaches, and that number that goes with it is 260. So we're going to put that in here first. 260 feet is the greatest height the rocket reaches. How long does it take the rocket to reach its maximum height? Well, if we find the maximum height and we see what time it is, it reaches its maximum height 4 seconds after launch. So at 4 seconds. Now, how about how high is the rocket after 1 second? Well, let's go back to our graph. We'll look at 1 second, and here's the point. It's somewhere between 110 and 120, so we're going to approximate it at about 115 seconds. And then finally, what is the domain and range of the function? Well, remember, your domain's your x, so your domain would be from 0 to 8, and your range would be from 0 to 260, since that's in your y. So the domain would be from 0 to 8, and your range would be from 0 to 260. And we do include both ends of your bounds in both your domain and range in this case. All right, well, it's nice that we had a graph for that first example, but what if we don't have a graph? What if we only have an equation, such as the one here in example 6? We can still find the information that we are looking for. So in example 6, a model rocket is launched from the roof of a building. Its flight path is modeled by this function, where h of t is the height of the rocket in meters above the ground and t is the time in seconds after launch. How tall is the building? Well, if you think about it, the building is where it's being launched from, and that's at time 0. Time 0 is along the y-axis. So if we are at the y-axis at launch and we're on top of the building, then we can use our y-intercept to find that. So using the y-intercept, we can find how tall the building is that the rocket is being launched from. And to do that, we're just going to plug in 0 for our time, because at time 0. We haven't launched it yet. We're still on top of the building. So when you plug in 0, and since we are talking about y-intercept and we're in standard form, you could probably already guessed that you can just pull it off of the end because it's your c value. So this 10 on the end is the only thing that will remain. So the height of the building is 10 meters. How long did it take for the rocket to reach its maximum height? Well, for this, we have to think about where the rocket is. If it's at its maximum height, then it's at the vertex of the parabola. And since time is along the x-axis, then we can find our axis of symmetry to find that x value, or in this case, it would be our t value. So in this case, it's t. Our axis of symmetry in standard form is found by negative b over 2a. b here is 30. a is negative 5. And so when you do this, we have 30 over 10, which ends up being 3. So it took 3 seconds for for it to reach its maximum height. And finally, what is the maximum height of the rocket? Well, to do this, we're just going to take the time that it's at the vertex to find out what the height is at the vertex. So we're just going to do h of 3 equals -5 times 3 squared, just plugging in our 3 as our time that it's at the maximum height. And so when you do this math, you end up with -45 plus 90 plus 10, which gives you 55. So 55 meters is the maximum height. So you'll notice finding these pieces of information aren't necessarily hard. It's not necessarily a lot of work. You just need to know what you're looking for each of those. And you need to know what point on the parabola you're at for each of these events. All right, let's look at example 7. As Molly dives into her pool, her height in feet above the water can be modeled by the function given here, where x is the time in seconds after she dives. How high is the diving board? Again, this is where she's starting, so we're at time 0. So we're going to put in f of 0. So essentially we're looking for our y-intercept. And since we're looking for our y-intercept, you can probably already identify that right off the end. It's our c value. So the height of the diving board is 12 feet. How long did it take for Molly to reach the maximum height of her dive? Again, we're looking for the x value for our vertex for time. So we're looking for our axis of symmetry, which is -b over 2a. b in this case is 16. A is -16. And so we have 16 over 32, which reduces to 1/2. So at 1/2 seconds, she reached the maximum height of her dive. And you want to ask yourself, does this make sense? Well, yes, it does, because when a diver goes off the diving board, they go up and very quickly come back down. They are not going up for a very long time. So 1/2 of a second does seem like it makes sense. And then if we want to know the maximum height of Molly's dive, you're going to take that time that she was at her maximum height, and you're going to plug that into your function. So -16, so we got 1/2 squared, which is 1/4. 16 divided by 4 is 4, so you have -4. 16 divided by 2 is 8. Then you have plus 12. And so you end up with 16 feet was the maximum height of her dive. Again, does this make sense? Well, yes, because she started at 12 feet. She goes to 16 feet. So she only goes up 4 feet before she comes back down. It does sound like that's a lot for a jump, but remember, diving boards are springy, so that gives her a little bit of a push up into the air. So it does make sense that she would go up about 4 feet before coming back down. All right, for this next example, the height in feet of a football that is kicked can be modeled by the function given here, where x is the time in seconds after it is kicked. What is the maximum height of the football? Well, the maximum height of the football can be found after we find the time that it reaches that maximum height, and we find the time by using our axis of symmetry. So -b over 2a, b is 64, a is -16, so you're going to end up with 64 over 32, and that is 2. So we're at 2 seconds. So if we want to find the height at 2 seconds, you're going to plug that in. And so in the first term, we end up with -64. 2 squared is 4. 4 times -16 is -64. 64 times 2 is 128. And so 64 feet, yes, feet, is the maximum height of the football. Now, how long was the football in the air? So for this one, you'll notice that there's no c value. There's no y-intercept, which means we're starting from the ground and we're ending from the ground. So it took 2 seconds for it to go from the ground to the maximum height. So it's going to take another 2 seconds, since parabolas are symmetrical, It's going to take another 2 seconds for it to go from its maximum height back down to the ground. So therefore, it would have been in the air for 4 seconds. Now you have to be careful because you can only use that method to find how long something's been in the air if it starts and stops at the same height. Okay, so in the previous 2 examples, you won't be able to do this because we're starting from an elevated height in both of those cases. And what is a reasonable domain and range for this? Well, our domain is our time, so that would be our 0 to 4 seconds. And our range is our height, and the maximum height was 64, so it goes from the surface, which is 0, to 64 feet. All right, one more example. A scientist records the motion of a dolphin as it jumps from the water. The function given here models the dolphin's height in feet above the water after t seconds. What is the maximum height of the dolphin? Again, we need to find the time it reaches the maximum height first. So we're going to do our axis of symmetry. So we have negative 32 over 2 times negative 16, which gives us 32 over 32, which equals 1. Then we're going to plug that back in for our height function. So that's going to be h of 1 equals negative 16 times 1 squared plus 32 times 1. So we have negative 16 plus 32, which means the maximum height from the dolphin is 16 feet. How long was the dolphin out of the water? Again, the dolphin starts at the water surface and ends at the water surface. So it took 1 second for it to get to the top of its path, another second for it to come down, so it was out of the water for 2 seconds. And then the domain would be our time, 0 to 2 seconds, and our range would be our height, which would be 0 to 16 feet. So that's just a little bit of applications on quadratics and how to actually use quadratic functions in a real-world sense. Okay, so this concludes section 2-3. The next section will be on using quadratics and inequalities.